radioactive decay and population growth. So this is just some examples for students that I'm teaching, but I'll share them with everybody. And what do they have in common, I guess? Well, one's exponential growth, one's exponential decay. And common problems you see in about any math text that deals with any algebra text. So here we go. We'll start with the population growth one. A town has a population of 22,600 in 1990 and a population of 24,200 in 1995. Find the exponential growth function that models the population for the town. Use the growth function to predict the population of the town in 2013. Round to the nearest person. So we'll go ahead and set this one up. So population growth will model with continuous growth, with a continuous growth model, which I always use the same kind of set of letters, but I always say A equals, I like PERT, P e to the RT, so E being the Euler number. So A represents our final amount, given a certain amount of time. P represents our initial amount. R represents our rate of growth, which in this case they don't give us, and we're going to have to find it. And T represents time in years in this case. Could be in days, and the next problem is going to be in days. But so that's kind of what all of that stuff means. So we'll go ahead and start plugging this in. Well, we know in 1990 the population was 22,600. We knew in 1995 the population is 24,200. And we need to create a model that represents this information so that we can predict accurately what the growth will be in 2013. Okay, so when we take a look at this, so we start plugging things in. And before I do that, I guess one thing that makes the problem a little easier is you could go ahead and let 1990 equals 0. Okay, so we'll let our initial amount of 90, our time will be 0 at 1990. So maybe I'll restate that. In 1990, let our time equal 0. All right, so that means in 1995 our time is 5. So we're ready to start plugging in. So in 1995 we ended up with 24,200, and let me kind of write the equation up here so you can kind of follow along what I'm doing. So that's our final amount. We began with 22,600 in E to the R. We don't know our rate, but we do know in 1995 that's 5 years after 1990. And so there's our kind of equation in order to find our rate of growth. So we're going to go ahead and solve this thing then for for R. Ugh. So you would divide both sides by 22,600 to get the exponent by itself. And hopefully you've looked at a couple of solving exponential equations videos where you figured that out, because this is now kind of the application side of it. And we know that 24,200 divided by 22,600 is 1.07. And so that equals E to the 5R. I don't like the R5. Okay, now to solve this, then we have an R. Our exponent is R, so we're going to have a natural log in here. So we'll natural log both sides, and so what that does is it pops out the 5R in front, but also ln and e are inverses of each other, so they eliminate or they become 1. And so we know that all we're left with on the right side is 5R, which makes it kind of convenient. And on the left side we have natural log of 1.07. So then it's just a matter of dividing by 5 on both sides, and we'll come up with our rate. And so we know R is approximately equal to the natural log of 1.07 divided by 5, which is approximately equal to 0.0135. So that's our rate of decay, or rate of growth, sorry. I'm jumping to the next problem already. So we can plug that into our model. So our new model reads something like this. So our total amount would be 22,600, because that's still our initial amount in 1990. E to the 0.0135 T. And so that gives us our model for any time, any year, throughout, whenever. And so now, 2013, we're ready to figure out what the population is in 2013. It says predict the population of the town in 2013. So, well, this is a little tricky because we let 1990 be 0. So we let time be 0. So 2013 to 1990 would be 13 from 2000 plus 10 more, or go ahead and subtract those two. So I'm kind of running out of room here, sorry. And so we would go ahead and subtract those two, so I'll do that down here. Yeah, so 2013 minus 1990 is 23 years have gone by. And so we can just plug that. That's going to be our time t. So in 2013 is 23 years after 1990. So our amount is going to be 22,600 e to the 0.0135 times 23. Oh, for goodness sakes. Let's try that again. E to the 0.0135 times 23. So now you can just get your calculator out and plug that in. And we end up with approximately, it says round to the nearest person, but approximately 30,829 people. So, you'd probably want to write that out as a sentence. There, in 2013, our model predicts there will be 30,829 people. So, there's one example using population growth. Now, let's look at the other side, which is decay. And we've got this situation I kind of looked up on the line. But polonium, didn't even know it existed, but it's an element that has a half-life of approximately 50 days. According to Wikipedia, a minimum lethal dose of polonium is said to be around 0.089 micrograms. If you think about a microgram, that's there's 1,000,000 micrograms in 1 gram. So this is a very small amount. If we have 1 microgram or 1/1,000,000th of a gram of polonium on hand, how long will it take to become a non-lethal amount? So below that 0.89. So the first thing you're going to have to figure out is the rate of decay. So the rate of decay is 50 days. So now we're not dealing with years anymore. And this is a decay function. So here we go. So again, our equation is PERT, because this is decaying continuously. This is our model that we're going to use. Same things apply, but the first thing we need to find is our rate. So let's just assume it's going to decay the same no matter how much material you have. So let's just say we have 1 ounce of polonium to start with, or 1 microgram. So that would be e to the RT. Oh, and sorry, we know time because time is 50 days. So times 50. So it's a half-life of 50 days. And half-life means when is it going to be half as much? So in 50 days, that 1 microgram will be a half a microgram. So you could also use that to kind of estimate your answer. You know, you just keep working backwards. So 1/4 would be 100 days. Um, one 1/8 would be 150 days. And so we're getting closer all the time. So we're probably around the 200-day mark if you wanted to estimate your answer. But anyway, we just need to solve this. So we've got an exponential equation. Hopefully you're getting pretty good at solving these by now. 1 times e to the 50r, you know, we can drop that 1. To solve for an exponential equation, we're going to natural log both sides. And again, so natural log of 1/2 is equal to 50r. And then you would divide by the 50. And so your rate of growth is natural log of 1/2 divided by 50. Now, that's the exact answer. Let's go ahead and approximate that. And approximately, that would be negative 0.014. Okay, then I need to hurry along because I don't have much time left. So now we have a model for this thing. And we know that we're going to end up, well, let me write my model first. So the amount A, and we did start with 1 microgram, so not that you need the 1 there, but I like to put it there, is times, you know, again, I'm using this, using PERT. So amount equals 1 e to the, instead of r now, we've got 0.014, and then times t, however many days, and t is in days, so keep that in mind, not years anymore. And we want to end up with the non-lethal, something below that 0.089 number. So that's the amount we have to be below. So we need something that is less than that. Not that the less than is real important here, but any amount less than that would be less than a lethal dose. And so you solve this like normal. Natural log both sides. And so you'd have natural log of 0.089 is less than E and ln. E and natural log invert each other, and so you're left with negative 0.014t. And then you divide by negative 0.014 on both sides of the equation. So t has to be less than this amount. And this is still an approximated amount because I approximated the rate of decay. But if you plug that in, t should be less than about 178 days. It gives you 177.7, but definitely needs to be below that. So that is a couple of examples, one for growth, one for decay. Kind of a half-life deal. A lot of times you think of half-life as being in thousands and thousands of years. Well, not all elements decay like that. I mean, for instance, a car decays at a rate of 25% a year. You know, each year there's a decay rate. So you could calculate your half-life of a car pretty quickly. iPods and computers probably decay much quicker than that. And so that's just kind of a great example of half-life. So I hope this helps. Hope this adds to your understanding of of growth and decay, and I will see you next time.